is quite similar to that of a modulation. As a matter of fact, what you really do is, if you call x of t, your message, times cosine omega ct to be equal to y of t, let's say, the modulated signal that has been transmitted, you take this and modulate once again with a cosine. This time let's call it z of t is equal to y of t times cosine omega ct, the same frequency. Of course, you need to know it then. Then what does it correspond to in frequency domain? It means y of j omega convolution with two impulses. Like this. I'm just omitting the scales here. There's a 1 over 2, there's a 1 over 2 pi, whatever they are, but this is the shape that you have. And therefore, you need to convolve that output Fourier transform again with two impulses. These two impulses are like an impulse here and here at omega minus omega c and plus omega c over the frequency axis. Now I ask you to convolve this signal, which is y of j omega, by the way, that one, with this one. How do you do that? Or let's start by convolving this thing with this impulse, the first impulse at the left-hand side. Let's start by doing that. How does it produce the output? What's the output that comes out? What is the convolution of this, these two triangles at the left and right, with this one? Again, the same shift. It doesn't need to be a baseband signal for the convolution. It can be a bandpass signal like this, and then what you're doing is you're just convolving with this impulse at minus omega c. So you need to shift these two triangles to the left-hand side by an amount of omega c. Then what is the shape that you get? If that signal is shifted towards left by an amount of omega c, you have this triangle and this triangle. This is at 0. This is at minus 2 omega c, right? Shifted further towards left. Now let's convolve those two triangles with this impulse. Then this time it corresponds to a shift to the right. And that will make, I'm looking for a colored chalk. Okay, let's draw it with this one. Those two triangles shifted towards right is producing this green triangle that is coming from the left-hand side, and the right-hand side triangle is here at or around 2 omega c, like this. So there are two components, the whites here, the green ones at the right-hand side. So this is the overall picture that you get. What's the summation of these two triangles, the white one and the green one? They are exactly the same shapes, by the way. So they are added to get a taller triangle, which is the same shape. It's just a scale. And I'm already ignoring the 1 over 2s and 1 over 2 pi's, everything. So this twice is just another scale. We don't care about scales in telecommunications because you can always amplify your sound by the volume. It's just a scale. We don't mind about that. The shape is important for us for telecommunications. So this is twice the same triangle in the center. But unfortunately, we have this tail at 2 omega c and this one at minus 2 omega c. How do we get rid of these? We insert or we input this z of t into an ideal low-pass filter. And the output is a scale a times the original x of t. So what we do is we low pass filter. The central portions are retained the tail portions are not passing from this low pass filter, and the output is this triangle, which is the original triangle in the beginning from minus W to W. So the mathematical modulation and demodulation effects are almost the same. You have to multiply with a cosine. That is demodulation, and this is amplitude modulation scheme that we're talking about. You will go into the details of such modulation techniques in telecommunications courses. All right. Now, the properties of Fourier transforms are usually these things that we have seen, and this was the last property. You may think of other questions, you may invent questions, or you may take a look at the questions in the book as well. Where else can I use, for example, this multiplication or modulation technique? You can use it for filtering. You can just multiply your signal x, not with a cosine, but with a complex exponential. A complex exponential will have only one impulse. So what does it correspond to in frequency domain? Convolution with an impulse. The convolution of that triangle with an impulse. It's just pushing, shifting this triangle to a particular position. That is modulation, basically. Then you apply a filter. So you are chopping off some tails of these triangles, for example. What is the overall effect that corresponds to that? Or after chopping off the tail, you may put it back by demodulation, convolution with another impulse, or multiplication with another complex exponential. Such questions may be invented. Let me briefly explain what I mean here, because this modulation is a typical example, but we haven't seen any other example. What I'm saying is this: if the Fourier transform of your signal is this, and when you convolve it with an impulse like this in Fourier domain, that happens by multiplying this with a complex exponential, then it is shifted here, the shape is shifted here. Then you apply a low pass filter, for example, and then apply demodulation. What is the result? The result is a weird tail of this triangle that comes from here. So effectively what you get is a high pass filtered version by applying a low pass filter, because you're applying a low pass filter here, but after modulation you apply the low pass filter, and what you get will be the high pass filtered version of the original. That's the effect that may be thought of. So such questions may be encountered, including the examination. Now, it's not a property that I'm going to talk about, but it's the utilization of a property in Fourier domain that we will see now, which is the last thing that we will see for continuous time Fourier transform. And that is the linear differential equations. And in this way of visualizing linear differential equations, we are not going to solve the differential equation for the particular case. We don't have any initial conditions or anything. We will just find the homogeneous part of the solution, which is the natural response of the filter effect for the input-output characteristics. What are those filters, or what are those input-output characteristics that are described by differential equations? Let's start with an example. The derivative of y of t is equal or plus a times y of t is equal to x of t, for example. And I'm not giving you the initial conditions or anything, so we are not interested in the particular solution. How do we solve this, or what is the behavior of this thing if it is a filter? And by the way, if anything is described as a set of linear differential equations like this, then it corresponds to an LTI system. There is an LTI filter, a system, which has this input-output characteristics. That input-output characteristics is also available in discrete time as well, and we have seen such a question in the first midterm. There was a difference equation, and I wanted you to solve it. It is possible to solve difference equations in discrete time iteratively because they are with integer time indices, but if it's a differential equation, you cannot apply an impulse and observe the output. Can you do that here? You can't do that. You can only do that in discrete time, or you should be able to do that in discrete time. But this is also a linear system. What is the impulse response of this linear system is the question, without considering any initial conditions. And the way to solve it from differential equations, you already know that whenever you have d by dt, you put an s. You know that. So the situation is no different than that. You just take the Fourier transform of both sides of the equation, and with an s, it's not the Fourier transform, but it's the Laplace transform. We will see that. It's even easier than the Fourier transform, but with the Fourier transform, it's still possible. So let's take the Fourier transform of this equation from both sides. And we know that if you have a derivative, that corresponds to multiplication with the j omega, y of j omega, plus a times y of j omega is equal to x of j omega. That's it. I have taken the Fourier transform of both sides of the equation, and I'm using the linearity property of Fourier transform. Then the system that we're looking for is like this. We have a y of j omega in parentheses, j omega plus a is equal to x of j omega. Now, do you remember that if x of t comes into a system, the output is y of t, means x of t convolution h of t is equal to y of t. And from the convolution property, that is x of j omega times h of j omega is equal to y of j omega. This is something that we just saw last hour, which makes h of j omega to be equal to y of j omega divided by x of j omega. So this ratio is the definition of the frequency response. But that ratio, y over x, is only valid in Fourier domain. Okay, it's not valid in time domain. You cannot say h of t is equal to y of t over x of t. That's not possible. There's no such thing, because xt and y of t and h of t are related with a convolution, not with a multiplication. But in the Fourier domain, that's a multiplication. So h of j omega is equal to y of j omega over x of j omega. So what is y of j omega over x of j omega? From here, that is h of j omega, by the way, is equal to, what is that? 1 over j omega plus a. That's it. That is h of j omega. And does it resemble any of the Fourier transforms that we have seen before? Of course. So h of t is e to the minus at u of t. And you can nail it inside the box. So what did we find? We found the impulse response of our system. And interestingly, if there is a system with this impulse response, it corresponds to an input-output relation of this kind of a linear differential equation. Usually that's it. I mean, whenever you have a first-order differential equation, that first-order differential equation puts one exponential term. That is one exponential term. If that's a second-order differential equation, you will have two exponential terms. If it's a third order, then you will have three exponential terms like this one in the impulse response. So we are therefore having a three-way link. The first one is the impulse response. The second one was the frequency response. And the third one is the differential equation. And I can give you just any of these things. I can ask you a question which gives you the expression in any of these. And I can ask you any of the other. For example, I can give you this. The impulse response is this, I will say in the examination. And I will ask you the question, what is the differential equation which describes the input-output relation? And how are you going to do that? You will say that the Fourier transform of this is this, which is h of j omega, and that is y over x. Then multiply inside out, and you will get this equation, this expression. From this expression, you take the inverse Fourier transform and get this. And you will say that this is the differential equation. That's how you will do that. All right? So such questions may always exist. If it is not a first order differential equation, I must ask you questions very carefully, because differential equations of higher order will result in quadratic forms in the denominator of h of j omega, and the roots of a quadratic or a third order, etc., polynomials are rather difficult to evaluate, so they must correspond to some simple numbers. Otherwise, it will be a very difficult question for you. What I mean can be exemplified with this example. The second order differential equation. The second derivative of y of t plus 4 times the derivative of y of t plus 3 times y of t is equal to the derivative of x of t plus 2 times x of t. It may be a long equation like this, but the Fourier transform is not a big deal. Twice the derivative means twice multiplication by j omega, that is j omega square, y j omega, plus 4 times j omega times y of j omega, plus 3 times y of j omega is equal to j omega times x of j omega plus 2x of j omega. Just put everything into parentheses and obtain y over x, y j omega over x of j omega. That will give you h of j omega is equal to j omega plus 2 over j omega squared plus 4j omega plus 3. And now the question is, what is this? And how can we invert this? Usually there are polynomials of j omega in the numerator and in the denominator. If it is like this, higher than the first order in the denominator, what you really need to do is you have to find the first order roots of these things. Well, I'm going to give you write down the answer first, and then we will elaborate on that. If you're not very much comfortable with j omega, just put an s and then split it in that sense, okay? This expression is equal to a half of 1 over j omega plus 1 plus a half of 1 over j omega plus 3. But how do I do that? You find it by finding the roots of the denominator. You just need to find the roots of this thing and write it like this: a over the first root thing plus b over the second root, and then find a and b. And a and b will be 1 over 2 and 1 over 2, for example, technically. But these techniques require some calculus. Okay? Just need to be able to split this into first order items. Once you can do that, or if you can do that, then the inverse Fourier transform is a piece of cake. The inverse Fourier transform for the first term is a half e to the minus t u of t, and the inverse Fourier transform of the second term is a half e to the minus 3t u of t, and that is h of t. Now, in some cases, in some unfortunate cases that can be encountered, these roots can be complex. All right? That's possible. For example, the root here is j omega is equal to minus 1, which is a real root. But for some cases, j omega is equal to a plus jb, a complex root can be encountered. Don't fear from such observations. Just put that complex number here. And that's not a big issue. That's not a problem. Okay? For example, if you have j omega plus 0.5 plus 0.3j is in the denominator of the first order system, then you have e to the minus, in parentheses, 0.5 plus 0.3j t u of t will be your answer. And e to the 0.3jt, what is that? That's a sinusoid. It's a complex exponential. So it's the multiplication of two things. One real exponential like this, e to the minus t u of t, and a complex exponential. So the situation will be not a decaying real exponential like this anymore. It will be the multiplication of a real exponential and a complex exponential, which makes a damping sinusoid like this. Like this. So the result will be this sinusoid, decaying or damping sinusoid. So don't be scared of observations which produces something complex here. That's possible because this is a quadratic formula, and a quadratic formula can easily have a complex root or two complex roots like this. So I'm not going into the details of a third order example because they are not related with the concept anymore. The concept is this much. If it's a third order thing, then you will have a third order denominator. And how do you find the roots of a third order polynomial? In general, there is no specific way. The easiest way is by inspection. You find the root, isolate one of the roots, you can see one of the roots, then put it into a parenthesis of the root and make the rest a quadratic form, and then find the roots of those things. Okay, that goes on like that. But that's mostly calculus or calculation skills. It's not signal processing skills anymore. But you always need calculation and mathematical skills for giving answers to signal processing questions like this one. So this is the idea here. Okay. Probably I'm going to give you the impulse response, and I'm going to ask you the differential equation which governs this thing. Or I'm going to give you the differential equation and ask you the impulse response. By the way, if you take a look at the first videos, or if you take a look at the first few pages of your notes, I gave you linear time invariant systems, or I gave you systems of mechanics and circuits. You remember that? There were examples of RLC circuits or oscillator damper mechanical systems. Those things were giving you differential equations, and we wrote down some of those differential equations over there. You remember that? Find the impulse responses from there. Because I'm going to ask it, of course. That's a very typical exam question. There's no way to avoid a circuit or a mechanical system question in the second midterm. Certainly there's going to be a layout, and I'm going to ask you the impulse response. Okay, now a new chapter, and tomorrow we will continue with this new chapter as much as possible, and in the second midterm we will be trying to include as much as possible from that chapter as well. And it's not a very difficult or a very different chapter. It's the discrete time Fourier transform. Just like first seeing the Fourier series coefficients of continuous time periodic signals and then discrete time Fourier series. Now we saw continuous time Fourier transform. It's time for discrete time Fourier transform. And I'm just going to omit all the details of the observations or the derivations. I'm just going to say that the discrete time Fourier transform is this. Do you remember the filtering of a discrete time signal with a discrete time linear time invariant system, and the output is y of n? If the Fourier series coefficients of this discrete time signal, I'm assuming that they are periodic. If the Fourier series coefficients are AKs, and the Fourier series coefficients here are BKs. What was BK? BK was equal to AK times this thing, h of omega. But I'm writing h of omega in a very hard way here. I'm writing it like e to the j omega. But e and j, as I said before, are just fixed numbers. E is the natural exponential term, it's a number, and j is the square root of -1. So this is a function of omega only, evaluated at omega is equal to k times omega 0. Omega 0 is the fundamental frequency. So we were expressing, what I'm trying to say is that we were expressing this filter as h of e to the j omega then. Okay, if you take a look at your notes, you will see that. The difference between the continuous time Fourier transform and the discrete time Fourier transform is therefore due to the notation as well. The Fourier transform this time will be x of e to the j omega, not x of j omega. X of j omega is the Fourier transform of x of t. X of e to the j omega is the Fourier transform of x of n. And if you remember the relation of h of e to the j omega in terms of h of n, the same relation exists here. X of e to the j omega is equal to summation n from minus infinity to infinity x of n e to the minus j omega n. This is the discrete time Fourier transform formula, and it is the same formula of h of e to the j omega in terms of h of n, by the way. So how did we describe, or how did we get this formula of h of e to the j omega? We applied an e to the j omega n as the input, and at the output we observed e to the j omega n times something. That times something was h of e to the j omega. So that is the Fourier transform of h of n, and it was valid for a system h of n. Now I'm telling you that it is also valid for the signal itself. If the signal is x of n, then the discrete time Fourier transform of a discrete signal is x of e to the j omega. And please also remember what I was telling you about the way this h of e to the j omega was looking like. Do you remember that? Do you remember the most important property of h of e to the j omega? It was 2 pi periodic. Because the Fourier series coefficients were repeating themselves. These were periodic. So this one was also periodic. As a matter of fact, that's why we write it as h of e to the j omega, not as h of j omega. Because e to the j omega is 2 pi periodic by omega. And as a result, the most important observation we must repeat. That is, e to the j omega is always 2 pi periodic. Okay. So this is the first check that you need to do. We will use this formula to find the Fourier transform of some of the discrete time signals. And then we will see some properties. We will solve a few problems. And then we will ask you exam questions. What is the discrete time Fourier transform of this, for example? You come up with an expression. You will come up with an expression. Please check it. Is the expression that you get 2 pi periodic or not? If it doesn't look like 2 pi periodic, then probably you found something wrong. It must be 2 pi periodic. Okay, that's an important property that must be satisfied always. We will come back to that. And the inversion. This inversion formula is again by multiplying both sides of this equation by the conjugate of this complex exponential, and then integrating both sides of the equation and cancelling some of the terms, we come up with eventually this formula. Which is the inverse discrete time Fourier transform. Does it resemble the inverse Fourier transform in continuous time? It really resembles that. In the continuous case, it was x of j omega e to the j omega t d omega. This time it is x of e to the j omega, which is the representation only, e to the j omega, not t but n, d omega. Same thing. Almost. This time, however, the integration is from minus pi to pi. And it doesn't really need to be from minus pi to pi. It's just a duration of 2 pi. So let's write it like this. It could be from 0 to 2 pi as well. The duration of the integral must be 2 pi. That's the only thing. It can be from minus pi to pi. It can be from minus 2 pi to 0. That's also possible. So the conjugate property of the forward transform and the inverse transform is still there. In the forward transform, there's a negative complex exponential, e to the minus j omega t, e to the minus j omega n. And in the inverse transform, you multiply with an e to the plus j omega t or e to the plus j omega n. A similar inversion formula is valid here. And for today, let's see at least one example, which is not a very difficult one, of what is the discrete time Fourier transform of an exponential. And such questions are too easy that they can be found using the formula only. Just apply it inside the summation. The Fourier transform is n from minus infinity to infinity, x of n, which is a to the n u of n, times e to the minus j omega n. All right? Is equal to, because of this u of n, it forces this summation to start from 0, because u of n is 0 for all n numbers less than 0. And for all n greater than 0, u of n is simply 1. So let's start by n is equal to 0, go to infinity. Now this thing becomes 1, and we have a to the n, e to the minus j omega n. The exponent of n is common here, and we can put into parentheses like this: a e to the minus j omega to the power n. Is it possible? Okay. So this is it. And that is this a times e to the j omega, whatever it is. Just call it, just give a name to it. Let's call it f. So it is f to the n. Summation from 0 to infinity, f to the n. We know what it is, right? It's an infinite power summation. What is that equal to? If this is f, yeah, it is 1 over 1 minus f. And that is 1 over 1 minus a e to the minus j omega. And that's it, finished. This is the Fourier transform. Do you remember the first thing that I asked you to check? Is it 2 pi periodic? Well, a nice way to check whether your observation is 2 pi periodic or not is to look at the expression and look for complex exponentials of e to the j omega or e to the minus j omega. If it is like e to the j omega, e to the j2 omega, 3 omega, whatever, if they are in that form, if there exists some terms like that, they are always 2 pi periodic. E to the minus j omega is always 2 pi periodic. Since this portion is a function of omega and it is 2 pi periodic, everything is 2 pi periodic. Okay? So the checklist number 1 is okay. The second one, what does it look like? And under which, what circumstances does it converge? I mean, you directly give me the answer that it is 1 over 1 minus f, but it is valid only for some certain assumptions. If f is less than 1 in magnitude, otherwise it will be a growing exponential, right? And the result will not be 1 over 1 minus f. So this tells me that a times e to the minus j omega in magnitude must be less than 1. The magnitude of e to the j omega or e to the minus j omega is 1. It's a unit magnitude. A complex with a unit magnitude. It's a cosine square plus sine square, which is 1. So the magnitude of this one is the magnitude of a. And that must be less than 1. Otherwise, it doesn't converge. Then, in fact, it violates the Dirichlet condition. What was the Dirichlet condition? The square sum of the terms must converge. Here, it is diverging if a is greater than or equal to 1. So if it is less than 1, then this is a valid result. 1 over 1 minus f is a valid result, and this is what you get. I may ask you further to plot the magnitude of the Fourier transform, magnitude, and the angle of it. From the magnitude, you will have the information whether it's a low pass or a high pass or a band pass filter or a signal. From the angle, the information, we don't know the name, okay? But the angle plus the magnitude altogether will give you the overall expression anyway. And the magnitude looks like this. Since a is less than 1 in magnitude, but a can be a positive or a negative. Let's assume that a is positive 0.5 or something like that. If this is 0.5, what does the figure look like? When omega is 0, this becomes 1, and 1 over 1 minus 0.5 is 2. So it may be something like this, a level of 2. When omega is equal to pi, the highest frequency, by the way, what is e to the minus j omega? What is e to the minus j pi? It is minus 1. If it is minus 1, 1 over 1 minus minus 0.5 is 1 over 1 plus 0.5. And what is 1 over 1 plus 0.5? 1 over 1.5 in other words. What is that? 0.6 sort of thing. So it is some value like this. So you're going to draw it like this. Probably. I'm not very sure about the accuracy of this plot. But at pi, it goes down to 0.6. At 0, it goes up to 2. And at 2 pi, e to the j 2 pi is again 1. So you get back to 2. At 3 pi, it goes down to this level. At 4 pi, it goes up again. And that's why everything is 2 pi periodic like this. The magnitude, this is the magnitude that I'm drawing here, is also showing the 2 pi periodicity example. In general, by the way, this value is 1 over 1 minus a, and this value here is 1 over 1 plus a. Isn't it? If it is 0.5, it is 2 and 0.6, but for other values of a, this value is 1 over 1 minus a, this value is 1 over 1 plus a. So is it a low pass signal or a high pass signal? More. Which one is more? It's an all pass signal. It's everywhere, by the way. From 0 to 2 pi, it's never 0. So it's not a low pass. It's not a high pass. But it is more low pass than high pass because the low frequencies around 0 or around 2 pi are larger than around pi, which is the highest frequency. So it is more low pass. When a is positive, a to the n, what does it look like? It looks like a decaying sequence like this, isn't it? For example, 0.5 or 1, 0.5, 0.25, etc. It is decreasing like this if a is positive. If a is negative, what does the shape look like? Then this value, 1 over 1 plus a, will be a large number because a is negative. So the shape will be the opposite, like this. At pi it is larger, at 0 and 2 pi it is smaller, and at 3 pi it's again larger. This is for a greater than 0, this is for a less than 0 situation. What does the time signal look like for a less than 0? It's a negative number to the n. For example, minus 0.5 to the n. Minus 0.5 to the 0 is what? 1. To the 1 it is minus 0.5. Then plus 0.25. Then minus something. Then plus something. Then minus something. It looks like this. The situation is like this. If a is less than 0, the bottom figure. If a is greater than 0, it's the top figure. Now, which one is low frequency, which one is high frequency? The top one is low frequency because it's smooth, it's not oscillating like crazy. This one is 1 positive, 1 negative, 1 positive, 1 negative. So this one is high frequency, and its Fourier transform magnitude shows it. You can see it. At pi it has high value, at 0 it has low value. This is very high frequency. This one is lower frequency. At 0 it is high, at pi it is low. And this is the time signal for that. So by looking at the Fourier transform, you should be able to tell the frequency content of the signal. Is it high frequency? Is it low frequency? Okay? That kind of a separation is a critical intuition in signal analysis. We will see other examples with this one tomorrow in 1 hour, and that 1 hour will be included in the second midterm as well. So let's stop at this point.